We are going to restart. So during the last lectures, we have made some recalls on coding theory. We have seen that error correcting codes can be used to detect and even to correct information. And in the context of cryptography, we have seen that a message could be like encrypted by first encoding it, and Bob chooses a random noise of some weight below the capacity of the code. And this gives him the ciphertext. And Alice could use the decoding algorithm to decrypt. And this was the framework of McEliece. We have also seen that McEliece relies on two security assumptions. First, the syndrome decoding problem, which is an NP-complete problem. And second, that the family of code that you use, the binary GOPA codes, are indistinguishable among random codes, right? We have seen that this resulted in quite large key sizes. And we have seen that a lot of efforts trying to reduce this key size, either by switching the code or by introducing some structure, have failed, up to some paper in 2012, which was called QC-MDPC for quasi-cyclic moderate parity check codes, which was like the premises of BIKE. And so the rest of this lecture is going to focus on more recent construction, such as BIKE and HQC. So I will roughly present, I will not give all the details on BIKE and HQC, but I will give you the main components of them. And if you have any questions on some technical details, I think we won't have time to cover them here, but feel free to jump in and ask for some exercises in the lab session. Maybe I will take one of the exercises to give some more examples. We will see if we have the time. I don't really know, but yes, we are here for understanding stuff, so here we are. So more recent constructions. The first one I wanted to talk about is BIKE, which, as you may know, is one of the 3 candidates remaining in the 4th round of the NIST standardization process. And so you have like this paper with a numerous number of authors. I think we are something like a bit more than 15 authors in the BIKE submission. And this is due to the fact that when we submitted BIKE to the NIST, it was like the merge of already 3 existing algorithms. The first one was QC-MDPC from 2012. The second one was CAKE from 2016. And the third one was Ouroboros from 2017. I will give a bit more details on the difference between each version in the next slide. But here is the basic framework. You have Alice and Bob. Alice will start by generating a private key, which I denote by H0 and H1. And this specific notation here is here to denote that S is a set over F2. This is vector of length n and weight w. So Alice samples 2 vectors, H0, H1, of length n and weight w. Okay? And now I additionally ask for H0 to be invertible. And at some point, it should raise the question for you, what? How does a vector is invertible? Yeah, okay. So that's where we need a bit of math. This string R, which kind of be similar to lattices with different properties. Here, these will be polynomials with degree less than n and satisfying the relationship each time I have x to the n. This gives me -1 because we are reducing x to modulo x to the n plus 1. So it gives me -1. But as I work in binary, -1 and +1 are the same. So x to the n is 1, x to the n plus 1 is x to the n plus 2 is x squared, so. Okay. So back to our question. What does it mean for H0 to be invertible? It simply means that if I consider H and I write it, sorry, let me consider a vector V, which would be V0 up to Vn minus 1. I can equivalently define V as a polynomial, which will be V equal the sum of V0, Vi, x to the I, for I equal 0 to n minus 1. Okay? And now my definition of a vector being invertible makes sense. I will say that a vector V is invertible if when I take its polynomial representation, this polynomial is invertible in this ring. Okay? And I will also need this like vector to polynomial isomorphism to define vector multiplication. Okay, so keep that in mind. It's very important. As we will see, we also have like a matrix representation of it, but it's very convenient to switch either from vector to polynomials or to polynomials from polynomials to vector. Okay, we always do this constantly. And so, because H0 is invertible, I will just say that my public key will be H1 times the inverse of H0. And here, on top of the inversion of a vector, I need the multiplication of vectors. So if I have a vector u, which is u0 up to un minus 1, I would say that the vector u times the vector v is equal to the vector whose polynomial representation is the product of the two polynomials. Does it make sense? Yeah? Okay. I take the polynomial representation of u. I take the polynomial representation of v. I multiply polynomials u and v. I get a polynomial of degree 2n minus 1. And I reduce this mod x n plus 1. It gives me a vector of, it gives me a polynomial of degree less than n. And I turn that back into a vector. And I get my product of vectors. Okay? From vectors, polynomial, and vice versa. Right? It turns out that when we are working on this specific ring, you also have a matrix representation of this, where actually you can expand either vector as the matrix of the cyclic shifts of u or v, and you make the vector matrix multiplication. Anyway, inverting the polynomial h0 is the expensive part. Multiplying two polynomials is quite efficient. Yes? Why aren't we always working in this ring?
Yes. Even that in field.
Even?
In field.
Even in P?
Field. This is mode 3.
Oh, actually, it will be mode 2, but you can make this mode P if you prefer, yes.
So, what is the importance to work in the ring, not in
rather than with vectors? Usually in codes we are used to vectors and matrices, so that's why we work with vector and matrices. But you have like an isomorphism between this ring and the set of vectors that you have. So you can switch from one to another. It's up to you. If you prefer to write the system with polynomials, you are free to go, right? Here, I want to make it coherent with what I presented earlier, so I will stick to vectors. But you can use some polynomial representation. It's as you wish. Okay. Other questions? Right. So Alice's secret key would be H0, H1. Alice's public key would be H. So she sent H to Bob, along with the capacity of the code, which I call C. And Bob now wants to encrypt the message M to Alice. So we will take this message M. It will generate two errors that comes from the, you need to use the hash of the message. This is a bit technical, but you need to use the hash of the message as a source of randomness to generate the errors for security requirements. But anyway, you generate two errors, E0, E1, and what's important here, they're in blue, so they are still randomness. E0, E1 needs to be of weight T, okay? That's the important thing. Keep in mind that what we are basing everything upon is the McEliece framework, where you encode some message, and on top of it, you add an error of weight less than the error correction capability of the code. So the randomness here is an error that needs to be below the capacity of the code. And so what we are going to use, it's the Niederreiter version of it. We are going to compute the syndrome of this error by some matrix. Here you have the polynomial version, but you can think of it as C equal E0 plus E1 times H, which if I want like coding theory representation, it would be this matrix, identity, and the cyclic shifts of H. Okay? I can write this equation as a syndrome decoding problem instance. This is the syndrome of E0, E1 by this parity check matrix. I didn't go down through the whole way when I defined my polynomial multiplication, but I told you that you have a matrix representation of it. And what you have to be convinced about, it's when I write this, I mean, I take H, this is my vector H, and this strange operator here is just, I take the cyclic shifts just as before, and this is my matrix. Everything that wraps around this needs to be taken back here, okay? And when you multiply by E1, you will actually get the equivalent of the polynomial multiplication of E1 times H. You have to be convinced of it. If you're not convinced about this, I will have the time to convince you during the lab session. For the moment, just trust me. Doing this kind of circulant representation, circulant matrix with H, and when you multiply by a vector, you will get the equivalent of the polynomial multiplication of E1 and of E1 and H, sorry. Okay? We will do this manually in the lab session. So actually C is just the syndrome of the small weight error randomness that encodes your message by the parity check matrix defined by the public key. H is the public key. It defines the parity check matrix, and you take the syndrome of an error of low weight representing your message, and this gives you the ciphertext. This is exactly the framework of Niederreiter, except that Niederreiter used generalized Reed-Solomon codes. If you want to have the equivalent of McEliece with Niederreiter framework, you would have to use binary data codes. Here, we are using quasi-cyclic moderate density parity check codes. Okay? Why are we using quasi-cyclic moderate parity check code? Moderate density parity check code, sorry. Because if you use H0 and H1 to define your parity check matrix, the matrix defined by H0 and H1, as H0 and H1 have both small weight of the order the square root of the length, this matrix will be moderately dense, meaning it is quite sparse. A lot of zeros, a few ones. A number of ones, which is of the order the square root of n. Okay? This is a secret version of the parity check matrix. This is a public version of the parity check matrix. The disguised version of the code. If I need to make a parallel to lattice base, this is my good basis with which I can do many things. This is my bad basis with which I can not do that many things. Okay, so I have my ciphertext. I just send my ciphertext to Alice, and she needs to decrypt. How does she do that? Well, she used the bit flipping algorithm. You don't know what it is. It is a decoding algorithm. It is a real famous decoding algorithm. It has been out for many years. I think that it was used in the 50s or the 60s. I don't remember exactly. It was by Gallagher. It was to decode low density parity check codes, where the number of one here is constant, even fewer ones than for moderate density parity check codes. But it's a relatively efficient iterative decoding algorithm. And I will explain its behavior in 2 slides. The idea is just that when Alice receives the ciphertext, using some decoding algorithm, she can recover the error, E0 and E1. Okay, so now we are in a situation where both Alice and Bob know E0 and E1. Well, for security reasons, we are not going to use this as a key, as a symmetric key, right through. We are going to use a shared key which is derived from this. You are going to use like a XOR function or a PRNG with this input to get your resulting AES key. You will need to use E0 and E1 to derive an AES key. What you want to do here is it's what we call a key encapsulation mechanism. So the shared secret that you have exchanged, you are going to use this to derive a symmetric key, and then after this, you are going to use symmetric encryption. Okay? So this is the framework of BIKE, roughly. This is, in the original BIKE submission, this was the second version of BIKE. This was BIKE 2. This corresponds to the exact QCM paper back from 2012. And this is eventually the only remaining version of BIKE. The other have been discarded by the BIKE team. All right? Any question about this? Yes. Can you please use them?
On the Bob side of the computation part, what is that H function, I guess?
What is, sorry?
That cursive H function, E0, E1 equals to H of M, which belongs.
You mean this one?
Yeah.
Yeah, okay. When we do a key encapsulation mechanism, of course, the naive way is to use a public key encryption scheme. For example, we could use RSA. I would say, okay, on my side and my side only, I will generate a symmetric AES key. I will take your RSA public key. I will encrypt my AES key under your public key. Then I will send you the ciphertext. And with this ciphertext, I will send you my data encrypted under this very same AES key using the AES encryption algorithm. So I will send you both the ciphertext encrypting the key, the AES key under your public key, and I will send my data encrypted with our shared AES key. Then in order to decrypt, first you decapsulate the key. You use your private RSA key to retrieve my AES key, our now shared AES key, and you use the AES key to decrypt AES data. Okay? And now we are doing exactly the same, but it's no more RSA. So in the context of key encapsulation mechanism, Bob will not generate directly an AES key. He will use some randomness of his choosing, uniformly random. He uses this to derive E0, E1, representing the randomness. What's important here is it has to have low weight so that we are on an instance of the syndrome decoding problem. And when we use the syndrome decoding distribution, Alice can decrypt. And when she decrypts, she retrieved this derived randomness, E0, E1, that can be used as a seed for a PRNG, a pseudo-random number generator. And then we have our shared keys. Okay, does that answer the question? Right. Yeah, okay, it's my fault. This is not a message, okay? Think of it as a randomness. Think of it as a randomness. What's important here is that I want Alice to retrieve the same E0 and E1 that me, Bob, I have generated. And once we have the same data, we can derive the same shared key, okay? That's what makes stuff work.
Yeah, but so when you apply the hash function on the whatever seed, what is the guarantee that the E0 and E1 you get will have weight at most T? Like
very tight.
What is the guarantee that the weight will be at most T of E0 and E1 when we get?
Okay. Yeah. Good and tough question. Actually, there are no specification for SHA whatever 256 or 512 or again whatever. This will only gives you like a bit string. Okay. So you have like standard techniques when you are given bit strings to turn these bit strings into small weight vectors of length n for arbitrary t and n meeting some conditions. It's not that quite arbitrary because there are conditions, but it's not, it might seem not natural to turn 256-bit string into a vector of weight w or t and length n, but we have like efficient procedure to do this. You can find a one-to-one mapping between both sets. So yeah, an efficient way to do this. But actually, I said earlier, this is a framework. There is a lot of technical details I won't go through. This is part of these technical details. I don't want to like get lost into, and I know I'm going to lose the audience if I go into this mapping. But yeah, indeed, at some point we have to define this hash function that maps arbitrary elements to specific vectors of weight t and length n. We have this. Don't worry, we have this. This is quite efficient. This is a non-negligible cost, but it is quite efficient. We have this. But yes, again, that's a good question. You have to find such a hash function. We can build it from any hash function. Other questions? Right. So yeah, bike 2, also known as bike. And before being known as bike, as I said, we had 3 bike versions. So this is a slide taken from Raphael Mizoxi from April 2018, the first NIST conference, the first NIST standardization conference, where each team submitting an algorithm had the opportunity to present its algorithm, and Raphael went there and he presented this beautiful summary where in very compact slide, you get the intuition behind the 3 versions of byte. So as I said, this is byte 2, the remaining byte version. Byte 1 was cake, and byte 3 was Ouroboros. What's important here is that this was in 2012, this was the baseline. And we already knew by that time that what's really inefficient in QCM DPC is the polynomial inversion, when you take this H0 to the -1. Because H0, if you like inject the parameters, I think n is several thousand. I think it may be something like 7,000 for 128 bits. And you have maybe the weight, which should be somewhere around 128, maybe something like this. I don't remember exactly. But yeah, you have inversion that costs a lot in the key generation algorithm. So basically what you want to do, you want to make an improvement on the key generation algorithm to make your algorithm faster. And you have to make compromise for this. And one of the compromise that was proposed back in 2016 was cake, also known as byte 1, where actually you add another polynomial g. You still have H0, H1. You no longer have any restriction on H0 being invertible. You just have an additional polynomial g. And the public key will be g times H1, g times H0. The drawback of doing this is that you have to expand the information that you send when you send the ciphertext. And you can see that here, it was only one ring element, one polynomial, or one vector, if you prefer. Here, you have 2 components. You have 2 of them. So you have doubled the length of the ciphertext. You got rid from polynomial inversion, which is good, but you double the bandwidth usage, which is bad. But depending on the use case, this is a trade-off, right? And also, in order to decode, you use the very same bit flipping algorithm, which I will talk about in a minute. And finally, so one other thing is that here in the public key, you used to have only H, which is H1 times H0 inverse. So the public key in byte, you only need to send H. With cake, you need to send GH1 and GH2. This is 2 elements. You also double the public key, yes.
You can kind of ignore this.
I think it's random. As far as I can remember, this is random. The question was, this is random. I could be wrong. This might need to be double-checked. But essentially, you're not using G anymore, so you don't have to use properties on G specifically here, because what you want to decode here, S, it's when you do the math, it's C0, H0. C0 here, I think it has low weight. C1 has low weight. All this has somehow low weight, and you can use your bit flipping algorithm to decode this. So I would say that G is arbitrary. Again, it needs to be double checked. Well, so anyway, you double the ciphertext bandwidth usage, and you also double the public key bandwidth usage when transmitted. The third version, Ouroboros, is a bit different. You generate still H1, H0 at random. You also have a polynomial G, and you do this, identity here. Cyclic shifts of G, and you do H0, H1, or maybe it's the other way around. Yes, it's the other way around. H1, H0. And you transmit a syndrome here and this famous G. But G, you've just picked it random. So instead of sending the 7,000 or whatever big it is, you just need to send the seed that you have used to generate G. So this ring element can be represented as small as 256 bits. That's a huge improvement over cake. But you still have this syndrome, which is a complete ring element to send. So byte 2, you only have H to send. Byte 3, you have a syndrome plus a seed. Cake, you have 2 ring elements. This gives you a trade-off. Unfortunately, this trade-off is this seed stuff cannot be used for the ciphertext, whereas in cake, you have 2 ring elements to send. So again, you have double the bandwidth. And somehow, we needed to add modification to the bit flipping algorithm because actually we are making a decoding but a noisy version of it. And actually, when you decode this, one of the stop conditions of the bit flipping is that you get to a null syndrome, and you have a code word, and you can find the message. Here, you are not quite getting a code word. You are getting a code word plus some noise. So we had to introduce like relaxation parameters to the bit flipping algorithm to make this work. This is the u equals 0, u equals 0, and u equals something different from 0. It's only here to mean that when we decode for cake and QCM-DPC by 2, we yield a code word, an exact code word. Here, we need to relax this parameter to allow for some noise to remain. But again, it's technicality. At the bottom line, all 3 algorithms use the bit flipping algorithm or a slightly modified version of it. So that's why the name BIKE, bit flipping algorithm, BI of BIKE is BI of bit flipping algorithm, and key A is for key encapsulation. We had to come with a sexy name, and it was BIKE. At the end, you get the error that was generated by Bob, and you can use this to derive a shared key. Okay? Which is like key derivation function of E0, E1. Okay, questions? 3 versions of BIKE. The only one still under consideration by NIST is BIKE 2, also called BIKE. Yes?
You take an assumption in the first line that your x to power r minus 1 over x minus 1 should be irreducible. So, what that assumption is doing actually, like?
What should be irreducible?
No, why you are taking an assumption like this?
We are only making like advised choices regarding that is the degree of the polynomial by which you quotient this ring. Because otherwise, if you take like n just as you wish, you can have folding attacks, meaning that you can split this xn plus 1 into a lot of polynomials and try to solve the problem of each subring and find and reassemble that to a global solution. So actually, in most summation using this ring, we have the choice that n is a primitive prime, which is a scientific appellation to say that x to the n plus 1 divided by x plus 1. Again, we are working mod 2, so x to the n plus 1 always have 1 as a root. So we can divide by x plus 1. We get x to the n minus 1 plus 1. This polynomial, if you take n, which is a primitive prime, this polynomial would be irreducible. Okay, this is the only like
Einstein criteria.
interesting choice for it. Does that answer the question?
Yes.
Yes. Okay. Great. Other questions?
An n there. If that is composite, what happens?
What happens if R is composite?
R or n, as you mean, like that's the quotient. In the quotient, x power n plus 1, let's say.
It is composite.
No, n is prime, right?
Yeah, but
So what happens if it is composite?
yeah, but x to the n plus 1 is always like a composite polynomial. You can always write it x plus 1 times x to the n minus 1 plus x to the n minus 2 plus 1. Okay?
Yeah, I meant the number
1
n.
is always a root of this polynomial.
Yeah, that is okay. I meant the number n, which is a prime number.
Oh, what happens if
that
n
number,
is composite?
number n.
Oh, bad things happen. Folding attack. Yeah, it doesn't work here. Of these polynomials, assume it splits into thousands of subrings. Then you can solve really tiny instances over these very small rings. You can solve them super efficiently. And then with Shining remainders strategies, you can get back to the, efficiently to a solution to your original problem. This is what I mean by bad things happen. Yeah, not a good choice, definitely. Other questions? Okay, great. So yes, 3-byte version using properties first. Key latency regarding key generation, as I said, byte 2 used to be somewhat inefficient in the key generation process. This has been incredibly improved and amortized, meaning that now byte key generation algorithm is not quite efficient, but it's not as inefficient as it used to be. So it's kind of still cumbersome, but it's acceptable, right? While byte 1 and byte 3 were super efficient. Communication, byte 1 and byte 3, it was only one polynomial multiplication. Okay, so it was super efficient. In terms of communication, for message 1, which is the public key, for byte 2, you had to send one ring element. For byte 3, you have to send one ring element plus a seed, which is 256 bits. And for byte 1, you have to send 2 ring elements, which is kind of more costly. For the ciphertext, there's only byte 2, which is efficient with one ring element. The byte 1 and byte 3 send both 2 elements. Regarding the decoding, as I was saying, you have the exact bit flipping decoding version for byte 1, byte 2, and you have a noisy bit flipping decoding algorithm for byte 3, right? And regarding the security properties, what was, in my opinion, really interesting in byte 3 is that you kind of rely on only one assumption, which was the syndrome decoding problem is hard for some specific quasi-cyclic codes, okay, of index 2 and 3. Whereas for byte 1 and byte 2, you have that this syndrome decoding problem is hard for quasi-cyclics of index 2, quasi-cyclic codes of index 2, but you also have similar problem, code word finding for quasi-cyclic codes of the same index, right? So you kind of have 2 security assumptions instead of 1. We had long discussions inside the byte team when NIST asked us to reduce the number of versions of byte. Which one? We are allowed to keep only one. Which one do we choose? There was no consensus, but eventually it was at this time that byte 2 key generation was severely improved, and eventually we decided to keep byte 2 and drop byte 1, byte 3. But yes, you have like the whole picture of the byte suit. As I said, they all use the bit flipping algorithm from Gallagher 63, so it was during the 60s. Essentially, remember when you use the parity check matrix, what you get when you compute a syndrome is satisfied and unsatisfied parity check equations. Yes, you remember Hamming code, where you had like these 3 parity check equations. the same way that having designed this code, we have like a bit more parity check equation because the matrices are much bigger than what we have done by hand. But anyway, what you do is you compute the syndrome of the error. You get a syndrome. In input, you have this syndrome, this parity check matrix, and you look at the number of unsatisfied parity check equations. And what you want to do is iteratively correct bits that meets this condition. You flip bits associated with most unsatisfied parity check equations. So when you look at the matrix, you say, okay, this bit is involved with this equation, this equation, and this one. So this is a total of 4 equations. This bit is only involved in 1 equation that is unsatisfied. This one is not involved with any equation that is unsatisfied. So your max is 4, so you are going to flip this bit first, okay? You flip the bits that are that correspond to the most unsatisfied number of parity check equations. And progressively, you decrease this number of unsatisfied parity check equations. That's why it's an iterative decoding algorithm. It is quite efficient, but there's a caveat to this. I think I will go back to this caveat a bit later. And at some point, the bit flipping, the exact decoding, bit flipping decoding algorithm successfully terminates if syndrome is 0. Otherwise, you have to repeat. The caveat here with this decoding algorithm is that, of course, the decoding failure rate is small enough for practical purposes. And usually, if you want to decrease this decryption failure rate, it's quite easy. You just adjust the parameter. What is kind of hard with this kind of algorithm is to make a full theoretical analysis of the decryption failure rate, simply because it is iterative and you don't know how many exactly errors do you correct at each step. So in sort of speaking, you have no guarantees of the number of errors you remove at each iteration. Okay? And because you don't have this, you only work with probabilities. When you iterate over this, this quickly becomes intractable to make a full theoretical analysis of the decryption failure rate. Okay, why do I spend so much time on decryption failure rate? Why is this so important? It's simply because there is a huge line of work on exploiting decryption failures to mount attacks against chems. Okay? The goal of the adversary is to mess with the plain text, to mess with the randomness, to mess with the keys, to mess with the scheme in order to get a decryption failure. And by obtaining a decryption failure, he learns some information on the secret key. Okay, so decryption failures are quite severe, are quite dangerous for schemes. That's the caveat of Bike, because right now there is no proof, no rigorous full theoretical analysis that the decryption failure is below 2 to the minus lambda, where lambda is your security parameters. There are evidences that it should be the case, but there is no proof yet. Well, and the rest was like back in 2018, some of us were working on improving this decoding algorithm, so we were also presenting this in NIST. Well, we've done Bike. If you have questions on Bike, this is the moment. In the lab session, we can try to implement this bit flipping algorithm. It's quite simple to implement, actually, unless you want super efficient stuff and with a decryption failure rate, which is like super slow. But yeah, you will see it's quite funny to implement the bit flipping decoding algorithm. So if you have any question on Bike, maybe it's here or during the lab session. No, I think I will skip to HQC, which is like the other algorithm, code-based crypto system of the 4th round. I did not mention classic McEliece, and I won't go through classic McEliece. If you have questions, Peter is here, but I can also answer. You're in classic McEliece, right? And so if you have any questions, you can direct them to me or Peter. But yeah, anyway, I think classic McEliece is just like the old version of McEliece you've seen. In classic McEliece, they don't use McEliece, they use Niederreiter, and they don't use this 62 bits version nor the 696 bits version. I don't remember exactly what was the security level in the original 78 McEliece submission, paper. They have like upscaled the parameters to meet NIST security levels 1, 3, and 5, which are roughly 128, 192, and 256 bits of security. Okay. So yeah, that's classic McEliece. I just introduced Bike, and I will skip to HQC. Yes, Alice.
Now I'm wondering, this looks like structured lattices. Is classic McEliece using non-structured, like Bike use structured codes with polynomials? Classic McEliece, is it using also polynomials and structured codes, or is it not? And if it's not, is it much less efficient than Bike then?
Okay, so the only thing it uses is binary GOPA codes, which are algebraic geometry codes. So you can construct these codes from curves. So you have some kind of structure for the family of code you are using. But the intuition is that binary GOPA codes are sufficiently many among the random codes. So there is a long belief that they are in this rate, they are it seems to be indistinguishable from random. It's not proven yet or disproved. But apart from this, there is no structure in classic McEliece. As you said, it might be like more Frodo or something. Yeah, classic McEliece remove the ring.
So is it less efficient than Bike?
So key generation is a disaster. It takes off the order a second, or even yeah. I have a slide on this, but it's not really up to date. But actually, key generation is the worst among code-based schemes, I think. But otherwise, McEliece has one super nice property is that it has ridiculously small ciphertext, and decapsulating is super efficient, crazily super efficient. It has the worst key generation efficiency. It has the best decapsulating efficiency. And for encapsulating, it really depends. It depends on the architecture also, but I have some comparison between them at the end. So eventually, if this does not answer the question, feel free to ask again at this point. So yeah, other questions? Great. To remember something that I said earlier. Okay, I won't do this part again, but at some point I said, when you are doing code-based cryptography, most of the time, the encoder is public, and you have to keep the decoder private, because otherwise the adversary who would have the decoder can remove the error himself and retrieve the message, right? Well, it's not the case for HQC. And actually, there was another scheme before HQC doing this. It was called Aleknovich scheme. It was back in 2003. It used random code, and it has super nice security reduction, but it used random code, so anyway, it was like super inefficient. In HQC, we departed from this work, Aleknovich, and we tried to inject like modern tools, like structures, and we managed to make this efficient using a public decoder. And what's super nice with this, if you use a public decoder, then it does not matter anymore what family of code you are using. What have been the long series of improvement tries and failures among the code-based encryption history was this one. Each time a new person came with a better proposition. Okay, so binary GOPA codes, they work, but they are not that good error correcting codes. Let's use generalized Reed-Solomon codes. Okay, it was Niederreiter, it failed. Let's use I don't know, alternate code, quasi codes. Everything failed because the disguised code was to be distinguished. With HQC, you no longer have this kind of ad hoc assumption. Okay, the code you are using is public, and its associated decoder is public, right? And in a few words, what's the intuition behind the fact that the adversary cannot decrypt a ciphertext is that, contrarily to McEliece and all encryption scheme around McEliece, when Bob encrypts his message, he's going to add a noise that is above the error capability of the code, not under. Meaning that anyone owning the decoding algorithm won't be able to do anything with this decoding algorithm. Only the knowledge of the private key will allow to remove from the ciphertext sufficiently many errors to go back under the error correction capability of the code. Okay, this is the intuition behind it. And if you have this intuition, it will become quite clear when I present HQC. So yeah, HQC, just take your favorite linear code. I will call this its generator matrix G. It can be a generator matrix of any code C, okay? Any code C. And you have, of course, an associated error correction capability. I denote this by T, sorry. And I also have an efficient decoding algorithm, but this time it is public. It is in green, right? It's no longer in red. The decoding algorithm is public. I compute two low-weight vectors of length n. Let's say they have weight w. I compute at random a vector h. So this one not necessarily have low weight. It has a random weight, n over 2 on average. And I compute the syndrome of my private key with respect to the parity check matrix induced by my public key. Not the public key. Let's say that H is part of the public key. It will define the parity check matrix, identity, and cyclic shifts of H. Okay? My secret key here is equal to X and Y, each of them having low weight. And I take the syndrome of my private key, SK, here. And this gives me what I call the syndrome S, which is X plus Y times H, or H times Y. It's commutative. Okay? Right. Now you send your public key. As a side note, T is just an integer. It's the error capability of the code. S is a looking random ring element, so you have to send it. And H is simply a random element that you just freshly generated. So if you don't want to send H in full, as a full ring element, you can just send a seed. Okay, 256 bits. Sorry, questions? Bob wants to send a message M to Alice. As before, it will generate some randomness, errors of the weight. We are going to pick first the syndrome of the two first parts of the error. I call this C0. And then I will encode my message M into M times G. And I will add some error here. Okay? What is super important here to notice is that C1 is equal to the message plus SR2 plus E. Okay? And now I have to stop for a minute and comment this out. The first comment I want to make is that although it might not be the case, this is very close to McEliece. If you want to be convinced of this, let me just call this E tilde. And then the equation becomes NG plus E tilde, right? Just as in McEliece. Okay. Remember my claim. For security to hold, as the decoder is public, we need to encode a message and add on top of it an error whose weight is above the error capability of the code. Okay? Is this the case? Well, this has weight T. This has weight T. Okay, what is the weight, the Hamming weight of S? Okay, once at a time, yes. Yes, yes, that's the definition. How many non-zero coordinates does S have? Sorry, who was the other one trying a guess? No? Okay. Sorry? Say again, I didn't hear. S?
Less than T.
Okay, let me just write that S is equal to X plus Y times H. Okay, so what is the weight of X? It's T. What is the weight of Y? It's T. What is the weight of H? We don't know. H is random. But as we are working in binary and H is random, we can say fairly that on average, H has weight n over 2, right? So what is the weight of this? It's going to be something of weight, roughly n over 2, plus some bigger discrepancy than with H, but still it's going to be fairly around n over 2. And what is the weight of S, the sum of this? Roughly, slightly bigger discrepancy is going to be n over 2. Okay? You do this polynomial stuff. You multiply this polynomial with S being a polynomial with a large number of non-zero monomials. So this one here has a huge weight, roughly. So basically, as the same applies for S, the same applies for this part, roughly this part has weight n over 2. Okay, roughly. But when you instantiate HQC, what's important here is that with an overwhelming probability between T and n over 2, there is a huge gap. So even if you are n over 2 minus 10T, I don't know, I didn't do the math, it's still going to be large, right? And it's still going to be over over T, the error capability of the code. So an adversary won't be able to decode this part. Okay? It's super important to notice that this is an error that we add on top of a message, an encoding message, but no one can use only the public decoder to remove this error, right? Well, that's the first remark. Is that, okay, it seems cool, And it would be cool if you are indeed able to remove this error, right? Otherwise, it's useless. At some point, you want to be able to decrypt. So, fortunately, we are going to be able to decrypt because this error is constructed using some structure. Yes, S is part of the public key, but it is also the syndrome of the secret key. And we know the secret key as the legitimate recipient. Okay, so we are going to use this for decryption, sorry. So Bob sends, we will be able to perform decryption. Other questions? I don't wait. How does decryption work? You take C0, you take C1, and you multiply by wire. And you decode this. Why does this work? Okay, so C0 used to be E0 plus E1 times H, and we are removing C1 plus SR2 plus E times Y. Okay? So this is E0 plus E1H minus MGY. I left the transpose aside, right? There are some transpose here to be correct. Okay, plus S used to be X plus Y times H times Y. I think there's going to be something wrong. Plus E. This is minus. This is minus EY. I changed the notation at the last time to be consistent with previous things. I think it was a bad idea. So, yes. So, you got E0 plus E1 and H minus MGY minus X. I'm worried because I changed the notation and it does not look familiar, this equation. So I think I made a mistake. Yes, R2 is the old notation of the paper. So R2 is R2 is supposed to be E. Okay. Yeah, I should have changed the notation. Excuse me a second. E0 equal R1. Was it R0 or R1? Yeah. E1 equal R2 and E which was equal to E. Okay. It's just a different in notation. And sometimes the order of this notation to be consistent with byte notation, they have been reverted. So, yeah. I will just skip with this. So C0 used to be R1 plus R2 times H. C1 used to be MG plus SR2 plus E. and you send both parts to the recipient, and you did like C1 minus C0y. Okay? I'm sorry, I've changed the notation at the last time. Mistake. So this one is mg plus SR2 plus E plus minus, sorry, R2 minus, sorry, R1 plus R2HY. Okay. So this is mg plus SR2 plus E minus R1Y minus R2HY. And now, sorry, I will continue here. So now I want to extend S into X plus H times Y. So this is mg plus XR2 plus this was YH times R2 plus E minus R1Y minus R2HY. Okay. This sounds familiar. And what's interesting here, we are working with polynomials whose coefficients are over a field. So everything here is commutative, and here also. So this part simplifies. Here, here. And what we are left with is mg plus some error, which is XR2 minus R1Y plus E. Okay. But now, what's interesting is that doing this adds a huge weight because there is H, which is random in it. So this part has a huge weight. This part has a huge weight. They vanish together.
Okay.
Actually, I would say, if you want the most versatile version of HUC that probably NIST won't accept to standardize as is, you could just say, let's standardize the framework and let people choose their favorite codes. In this case, you would have to specify what your T is. In the context of NIST, if HUC gets standardized, I think they will come up with their own code, maybe Reed-Solomon, maybe something else. And there, actually, yes, I think you won't have to send this T.
And probably also you're not sending the whole H, but you're sending some seed which you can expand on both sides, right?
Of course,
okay.
Of course. That's what's done in the specification, and that's how cats were generated.
Okay, thanks.
What?
R1Y plus Z. Okay, if you are assuming X as W, R2 as W, okay, and if I square it, I will get a W square minus W square, right? Plus W.
You
it
mean,
will get.
No, okay. It could get even worse, actually.
Okay, okay.
It could even get worse. Let me just end wave like this. Let's assume for a moment that this is XR2. It only has one here, and the rest is 0. Let's assume that this is R1Y. with one only here and here, when you do the difference, what you will get is here, is something like this. Okay? So adding a word of weight, anything minus a weight, a vector was the same weight, it won't vanish. It can, in the worst case, you double the weight. The intuition is when you do a product, you multiply the weight. Let's say this has weight A, this has weight B. The weight of the product will be AB at most. If this is A and B, the same holds for this. At most A times B. So this is at most 2 times AB. And so far. Yeah, okay. Great. I suggest that we just go through a quick comparison. Oh, it's not working anymore. Yeah, okay. So in this comparison, you will see the public key size in the y-axis. It's in bytes. And you will see the key generation time on the x-axis. It's in cycles. Okay? And both axes are logarithmic axes. So the data comes from Supercorp, which was like a benchmarking platform. And you have this kind of results. So I'm not expecting you to like read where McEliece is, read where bike is, read where HQC is. I did this for you. Classic McEliece is here. So you can see that in terms of public key size, upper is worse. And in terms of key generation time, rightmost is worse. Okay? And so classic McEliece is on top, the rightmost. So basically, it has the biggest public keys of the whole competition, except for post-quantum RSA. And it also has the worst key generation time. Anyway, bike is here, and HQC is here. So roughly, you can see that HQC's public key is about twice as big as bike, but it is significantly faster for the key generation. Why is that? Because you only have to compile with bike, you have to do this polynomial inversion. It has been efficient, but you can see that in comparison to classic McEliece, this is not free either. So this is public key size versus key generation time. We can do the same comparison with ciphertext size against encapsulation time. So the ciphertext size will be in the y-axis, and the encapsulation time will be on the x-axis. Still, it's a logarithmic scale, and we have classic McEliece, which has really tiny ciphertexts, and of course, the others are bigger. They were like the tiniest of the whole competition. That's the really good aspect with classic McEliece, and that's why a lot of people like this ciphertext size. And Bike and HQC have similar performance regarding encapsulation. Is kind of close to McEliece, classic McEliece in terms of decapsulation time, but again with larger ciphertexts. So this was for like software implementation, regular software implementation. Stuff can be better for hardware implementation. And if you look like, okay, I just put Psych for a reference. Psych has been like not withdrawn, but completely broken. You have HQC, classic McEliece Bike with the same security level. And you have a version which are lightweight for hardware implementation and high speed. You have kind of trade-offs to choose. And if you look at even key generation on constrained hardware, it's not that good for classic McEliece. I think there has been some improvement since then. They are 2022 results. But anyway, you can see that regarding the key generation, globally, HQC is really fast regarding the key generation. Regarding encapsulation, well, Bike and classic McEliece are similar, and it costs a lot more if you want a compact version on hardware, but it can be very efficient also if you want some high speed. And regarding decapsulation here, classic McEliece is outstanding, and for Bike and HQC, they can be like a huge trade-off, and they can have like be competitive with classic McEliece. Sometimes you are also interested in energy consumption, but I don't have the time for this. I have a summary here for like the properties. I would say in one word, in a few words, but in very low time. The main difference are the family of code that are both using. With classic McEliece, you are using algebraic codes in Hamming metric. With Bike and HQC, you are using structured code. There is no structure here. And the good point with classic McEliece is it has been outside for a long time. 1978. The classic McEliece submission is recent, but it's only the McEliece submission with a Niederreiter framework with updated parameters. So we can trust that it has the same security as the original McEliece framework. And yeah, I think I won't comment the rest. Everything is on the slide. You will have the slide. It's just a summary. I've already exceeded my time, so I will stop here. After the conclusion, the main conclusion is code-based crypto is ready and mature enough for standardization. I was asked earlier, do we have a proof that it is quantum safe? No, it's not quantum safe. We have an impact of quantum algorithm over code-based cryptography. For instance, Groover algorithm applies. So we need to carefully choose a parameter to discard Groover attack. But yeah, anyway, we have already techniques to reduce the key size, what was the main drawback of code-based cryptography. And we also have a secure approach to remove ad hoc assumptions such that indistinguishability of the family of code. And if you want to dig into code-based cryptography, there are several stuff you can do. Maybe some additional cryptanalysis implementation would be helpful. For instance, you have this decoding challenge site, which is online, so you can have a look to it. There are regular problem instantiation. There are NIST-like problems, so this is super useful. We already have some efficient and constant time decoder, but you can have either the efficient and constant time or the decryption failure rate, which is proven, but maybe it should be worth investing some time and effort into conciliating both. Of course, I would love to see proof that binary GOPA codes are indistinguishable for the range of parameters that we use in crypto, or the contrary, that disguised GOPA codes are indeed distinguishable from random codes. We still lack, as far as I know, a search-to-decision reduction from the decisional version of the quasi-cyclic syndrome decoding problem to a search version. And of course, there are other metrics in code-based crypto, such as rank metric or Lie metric. We will need more scrutiny for this alternative metric on code-based cryptography. And also, there are promising signature scheme. I did not have time to present this. I thought I would have time, but I didn't. And of course, a lot of scrutiny should be helpful for the unrun signature relying on code-based cryptography. Well, I also have a bunch of references. You will have all the references I used. I think there are 10 pages out of them, so I simply put all the references. You will have the slides, so you will have all these references, okay? So do not worry. You can find them back when you have the slides. Anyway, thank you very much for your attention, and thanks for your time. And if you